Hello, everybody. Today we will present you our field study, what we did on a real CO2 system, where we have ejector technology, and we will try to explain you what we gain by using this advanced technology in a medium-sized supermarket. My name is Mark. I'm global application expert for food retail, involved in the development of new solutions and new products for mainly CO2 systems. Together with me, it's Anya. Anya, please, can
Yes,
you introduce
yes,
yourself?
I can. Hello, everybody. My name is Anja Sofie Meiner Jensen. I'm also working with Mark in Danfoss food retail area. I'm a launch manager, meaning that I'm responsible for launching new products and technologies into the food retail area.
Thank you. So today we will go through system. We will explain technology, what we used, what solutions we are using. We will explain configuration, and what is most important is to present measurements and yearly analysis, what we did. And of course, at the end, there will be summary. The system what we will discuss today is a system which has a parallel compressor, which is activated when we have enough gas in the receiver, and then we are controlling the pressure in the receiver by using a parallel compressor. We also have a high pressure expansion valve, which is used to control pressure in the gas cooler, but also we have a combi ejector, which consists of two ejector technology. It's HP, or high pressure lift ejector, and liquid ejector. We will explain both of these technologies a bit more detailed. Then also we have a pack controller 782A, which is controlling compressors, gas cooler, of course heat recovery, which we also have in the system, and it's controlling the high pressure side in the gas cooler using both valves, ejector and high pressure expansion valve. And also the same controller is controlling gas bypass valve. Anya, can you present, please, those products?
Yes, I can, for sure. So here, for instance, we have the pack controller, the AKPC782A, as Mark just mentioned, and this is the brain in the system that is controlling the whole pack area. And a very key component when you want to have ejector solutions running. Another key component, especially when you have a combi block or any liquid ejector and you want to run the calm mode, is our case controller. Here we have the AKCC55 single coil case controller. And also the single coil will built-in UI is able to run with the liquid system, liquid in the system, meaning that in the case controller, we have developed a new algorithm that we call adaptive liquid control. And that is needed to run with the liquid in any systems and maximizing all evaporators. So that is the controller side of it. But of course, another very important side is, of course, our ejector. And here you see an example of a ejector cutaway model, where you actually can see how what is the inside of the ejector. Here first, you can see there's a built-in strainer, because in any system, of course, it's very important that the system is cleaned as possible. Then the ejector itself is here. So you can see what Mark will explain you is how the flows go in here, go to the chamber, go down here and move up the check valve, going into the mixing chamber, and then being pushed out here at the end. But of course, Mark will explain this much better than I did. But here you see the real product. And just to, of course, there was a demo model and a cutaway, but to have an idea of how the real ejector looks like, it looks like this. It is a 10-kilo baby, and it consists of 6 ejectors, one by one, as you can see. And in this case, we have 4 high pressure ejectors and 2 liquid ejectors. But just so you have an idea of how the product actually looks like in real life. So that was it for me.
Thank you. So In Danfoss, we have different ejectors, and you just saw the one which Anya showed you is this big block with the 6 ejectors. We also have a combination of 5 ejectors and 4 ejectors in the same block, but of course different capacities. And Anya also showed you this small block, which is intended for the liquid ejectors. And well, today we will focus on the one which is combination of high pressure and liquid ejectors, and all this built in the one big block. How it looks in the reality. This is the multi-flow. So high pressure ejectors, which are, let's say, if you go from the left to the right, are occupying these slots or cartridges, we often say, with the different capacities. And then as a first one in this line is a liquid ejector. In this case is liquid ejector 400. Let me explain the technology which is dedicated for different ejector design. So high pressure lift ejector is in general, it's intended to suck gas. Later on, I will explain you that this ejector can also lift the liquid, and we are utilizing both liquid ejector and high pressure lift ejector to manage liquid from the suction accumulator. But if we just focus on this technology, first of all, it's very important to know that this ejector is intended to enhance a system with parallel compressors. So if you don't have a parallel compressors, this is not the right ejector you can use. In a cold ambient condition, when the pressure in the gas cooler is low, there is not enough pressure drop across the ejector, so you will not gain any suction from the suction accumulator in this case. And in general, your system will work like a standard system, typically in wintertime when there is not enough gas in the receiver. And you can see in the log pH diagram, the gas is represented by this line here. There is not so many gas here, and then the system is working with controlling the pressure in the receiver with gas bypass valve, expanding the gas from this point here to the suction of empty compressors. If we have a higher ambient conditions, or we are typically in heat recovery mode when we are increasing pressure in the gas cooler, now we have a much higher pressure difference between this point here and what is the pressure in the receiver. And we are utilizing this high pressure difference or this high potential energy what we have in the gas cooler to take part of the flow from the suction of empty compressors, or in this case it is suction accumulator, and we are delivering this gas to the receiver. And this gas which is now in the receiver, and you can see now here we have this amount of gas in the receiver should be taken by the parallel compressors. So this is the reason why HP ejectors are dedicated to be used only in the system with the parallel compressors. The whole goal is not to take the whole flow from the empty compressors. The whole goal is to take the part of this flow, and we would like to maintain the operation of empty compressors, because running system in such a way we are enhancing efficiency to the maximum. What is important to know, in our PEC controller 782A, we have an algorithm where we are running optimal pressure in the receiver which is depending on the pressure in the gas cooler and what is the pressure in the suction of empty compressors. And we are constantly adjusting the pressure in the receiver to get the maximum efficiency of the system. So we don't have any more fixed value, but it's a floating value here. Liquid ejector system is the whole idea is a bit different. Here we are utilizing adaptive liquid control or the new developed superheat control for the evaporators to work, let's say, almost flooded. And in that way, we are maximizing efficiency of such evaporator. But when we are running with this very small superheat or even zero superheat, there are, of course, some drops of liquid which are going to the suction line, but we are controlling this amount on a very limited base. This liquid should be collected in the suction accumulator, and by liquid ejector, it is pumped directly to the receiver again. And of course, this liquid can be utilized for the evaporators again. Here is the goal when we are doing such a system when we are utilizing this surface of evaporator to the maximum, to increase evaporation pressure. And by doing this, we are making these empty compressors to run in a more efficient way. Coming to the point that this ejector can be used in a standard system. I mean a system where you don't have a parallel compressor, so it can be used in a normal booster system. It is also applicable for the liquid with the parallel compressor system. But what is the whole point is that liquid ejector is giving benefit to the system through the whole year. From other hand, when we know how high pressure ejector is designed and what is the purpose of it, it gives you benefits when the ambient temperature is warmer, typically above 16, 17 degrees Celsius, or when you have a heat recovery operation, because again, we are increasing the pressure in the gas cooler. But if we just apply a calm solution or the system which I will explain, just utilizing adaptive liquid control superheat, you will not gain all the benefits what we are explaining. The whole point is to adjust the suction pressure in the suction of empty compressor constantly. And we are doing this by utilizing let's say what we say a master control function. It is a P optimization, and this is a function which is implemented in our network unit named AKSM or System Manager 800. Today it's A version, to adjust reference pressure for the empty compressors according to the most loaded empty evaporators. And this process is going all year round. And then you are gaining benefits of this technology to optimizing operation of your empty compressors. Second point is that on these evaporators, we have to implement modulated thermostat control, not on-off control. And when we are applying such control, we are minimizing amount of liquid which will be delivered to the suction accumulator, because only the most loaded evaporators will operate with this zero LC superheat or at the minimum superheat, depending on the settings. So all these elements are essential for operation of calm solution. What will happen in case liquid ejector, in this case here is a symbol only of liquid ejector, is not capable to lift all the liquid what will be accumulated in this suction accumulator. The level will rise, and at certain point you have to have a level switch which will give a signal to the PEC controller, okay, we have too high level, and this level should be, in this case, in between green and yellow area. And when this switch will trigger, it will send information to the system manager. System manager will send information to all empty evaporators, stop with adaptive liquid control, superheat control, and move to the minimum stable superheat control, or in our world we can say normal DX system, because it will be dry expansion. There will be no any more liquid here going out. By doing this, you are stopping feeding the liquid to the suction accumulator and letting the system to get back to this green area, and then again when you will be below this level switch, together with, of course, some time delays, you will enable again to move to the adaptive liquid superheat control. Once again, all this process is combined, and we call it CO2 adaptive liquid management, or shortly CAM solution. One of the very often question is how much liquid is coming from the empty evaporators, how we can design our suction accumulator, what will be the reference. Here I would like to show you the measurements what we have, showing how many in percentages evaporators on this particular supermarket were in most loaded condition. And as you can see, very rarely this ratio is going above 30%. So this is something what we are using as a starting point for our calculation, how many liquid will be feed to the suction accumulator, because only from those evaporators you will get liquid out of them. This value will be multiplied with level of 10%, because the amount of liquid which is releasing from that particular evaporator is on the level of 10% of its capacity, mass flow. And you multiply this 30% by 10%, you are getting at the end 3% of the calculated liquid which potentially can go to the suction accumulator. And this value we are using to design, to size the suction accumulator. This calculation is valid for the supermarket, where we have a multiple similar size evaporators. When we are talking about more industrial installations, then we have to be more cautious, and then this value will not be relevant. We have to do it in a more way for each system to analyze how much liquid can potentially be released to the suction accumulator. Okay. Let's talk about this real system. We are talking about one supermarket in Germany, a supermarket chain, it's Edeka. The system started, let's say, at the end of 2019. The refrigeration load is 70 kilowatts on minus 10 degrees Celsius, 16 kilowatts on minus 32 degrees Celsius. On the gas cooler, or the high pressure side, we have also a three-way modulating valve, which is enabling us to completely bypass gas cooler when we are doing heat recovery operation. We also have a heat pump evaporator integrated in the gas cooler. When we need more heating in the system, we are applying this someone call it false load, to generate even more heat, because on this particular system there is no other additional energy heat source, but all the heat is coming from the refrigeration system. So concerning heat recovery, it's used for the space heating. Its capacity is designed for the 110 kilowatts, and when we are running heat recovery, we are going to the maximum 85 bars, not higher. The temperature which is used for the heating, we are using this level of 45-30 degrees Celsius range. If we are talking about our components on this side, and also the compressor size, they are sized in a way that the suction capacity is on the 93 kilowatts on empty suction line. We have one variable speed compressor and two fixed step compressors. There is one parallel compressor, variable speed drive. We have three LT compressors, one variable speed drive, and two step compressors. And as I mentioned, once again, these are the loads in the system. From Danfoss, we have a high pressure expansion valve, CCMT 16, mounted here. And there is a combi ejector, HP 2875 and liquid ejector 400. And it's all mounted in one block. And please note here, there is only one suction line going to the suction accumulator. And as I mentioned before, we are counting that the liquid ejector will be dominantly operation and dominantly responsible for the suction of liquid in the winter time. But in the summertime, we will also use, of course, HP ejectors to take gas and liquid to the receiver. So, as you can see here, this is a summer operation when we are going to the high pressure condition, and how this ratio of mass flows are split. If you imagine from the empty and IT compressors, you have, let's say, 100% mass flow going through the gas cooler. And on this point, we have 100% going to the combi ejector. If you imagine that this line goes vertically down, you can imagine that you always have a part of the gas you have to manage by your parallel compressors. But now in this case, it's the ratio is a bit different. So the 59% of after this expansion is a liquid. So this will be represented by this line here, from this point here to this point here. But 41% of the gas will be generated simply by this high pressure expansion process. But after this evaporation in empty and LT compressors, this 59% is coming to this part. And now the whole point utilizing a high pressure ejector is to take part of this flow, which is coming from this height here. And part in this case will be 32% of the total flow will be delivered to the receiver. 32 plus 41% equals to 73%. And this 73% of the mass flow should be taken by the parallel compressors. The rest of this flow, which is coming from the evaporators, should be taken by the empty compressors. In this case, is 27%. If you summarize again, this 27 plus 73%, you will get 100% of the mass flow. The system looks like this. you can notice this is a typical rack. You have here low temperature compressors, and here you have a medium and IT compressors mounted on the bottom. On this side here, you can notice this is a suction accumulator. And if you go to the point around this block, you can see a high pressure ejector, and you can see those cartridges mounted here, and of course a suction filter. Measurements. In this case, we extracted all the measurements which are related to the heat recovery, and with this analysis we were focusing on the system performance without heat recovery. And in that mode, we are always trying to maintain our pressure in the gas cooler according to this optimum COP line. And this scheme, this drawing you can find in all our manual related to the PEC controllers dealing with the CO2 systems. So this is what we consider as a normal system operation. If we are talking about system with the heat recovery, we are then generating more and more heat. And how we are doing this? First of all, you can imagine in the winter time we can be here with a low ambient condition in a low pressure in the gas cooler condition. First task is to increase the pressure. Second task is to decrease outlet temperature from the gas cooler. And when you are in this point here, this is kind of maximum heat recovery situation. Additionally, at the end of this process, we can also apply additional evaporator, which is mounted, as I mentioned at the beginning, next to the gas cooler. And this is, let's say, the maximum heat recovery condition. And once again, this operation mode is excluded from this analysis, what I will show you further on. How we did this analysis. So it's always a question, what is the system reference? And in this case, we have the same system, only what we are doing, we are switching on and off ejectors. On the left side, we have a system running with the standard system with utilizing parallel compressors. With this symbol, a red symbol, it's showing that the ejector are switched off, and also adaptive liquid control is switched off, so there is no benefits of getting this superheat control mode. So we are running like a standard IT operation system. On the right side, we switched on ejectors, and so we are utilizing liquid ejector technology and adaptive liquid control superheat, and also high pressure ejectors. So all this what I explained before. Next to this ejector, there is of course running high pressure ejector, but I put here a yellow sign. It's standing here and it's waiting to operate, but on this system, it was very visible that all the mass flow which is coming from the gas cooler was able to be covered or to managed by the combi ejector. In that case, this is the reason why I put it on a yellow sign. If ejector cannot manage all the mass flow coming from the gas cooler, the high pressure expansion valve will take the rest of the flow, and then those two valves will work in a parallel operation. Then we utilize weather measurements as one of the main elements how we analyze the system. And here is information about meteorological weather data, what we are gathering from the, let's say, official meteorological website nearby measured. And this is this blue line. Then with this orange color. These are ambient measurements measured below the gas cooler. So this is the entering temperature to the gas cooler. And then, okay, with this gray, I showed this how much differs these measurements between the, let's say, official meteorological data in the shadow and the measurements on the roof of the supermarket. And as you can see, these differences are between 1 to 2, maximum 3 kelvins through all this period. These colors are showing operation modes. So in the summertime, we did operation utilizing only high pressure ejectors. So we turn off adaptive liquid control operation. Then we switched off completely ejectors. So it was a standard operation system. And then in the wintertime, we worked together with the combi ejectors and utilizing both of these technologies, so HP and Calm solution. Why we are doing this? So always in the next diagrams, you will see ambient temperature on the x-axis and then different measurements on the epsilon axis. So black curve is showing trend line, how the empty evaporation temperature was changing according to the ambient temperature. So you can see that when the ambient temperature is getting less and less, the measurement what is in front of the empty compressor was slightly increasing because of this suction pressure optimization feature. By using a combi ejector, you can notice that during this process we had an increase of suction pressure between 2 and 2.5 kelvins in these lower ambient conditions. And this is what we are expecting, and what we are, you see the different direct benefit of using adaptive liquid control and ejectors operation. So this is what we are expecting. So besides this benefit, we also gain some other benefits. As you can see, the suction superheat is also lowered in a way that why is this happening? Because we are getting much more colder gas from this side when we are using adaptive liquid control superheat. And when you summarize all these flows coming to the suction of empty compressors, then you can notice that it's very visible trend that beside increasing the pressure ahead of empty compressors, we are also decreasing the temperature which is going in front of these empty compressors. And of course, this is giving you benefits in compressor operation. One thing which is expected, and this is what will happen with the LT compressor discharge discharge temperature / pressure, is it will increase. Why? Because we are increasing the pressure in this line here, and of course by increasing the pressure here, also your discharge pressure of the LT compressor will be increased. So this is a little drawback from this system, but in general, this increase is not significant as we are getting much more benefits on the MT and IT compressors you will see later on. But we are still on a very acceptable levels here. Regarding empty compressor discharge temperature, you can see, comparing to the standard system with parallel compressors and system with the ejectors operation, we have a decrease of the temperature. This is of course expected. Regarding parallel compressors, so this is the point here on the discharge line, you can notice in these curves, these lines are, let's say, completely aligned. What we see here, a little bit change from these trend curves, is something what is benefit. I mean, what is outcome of some measurements what we have, as you can notice here, these green dots, and I believe this is a result of residual temperature measurement when we are changing from the heat recovery operation to the normal operation. So there is a kind of residual measurements what we have here. But I believe when we'll have more measurement points, these lines will be aligned also in this area. And why is this so? Because these compressors are always taking gas which is on the saturated line in the receiver, and of course this gas should be heated up by this gas coming from the gas cooler. So in principle, condition for these compressors should be all the same. I mean, both operation the same. You have to have this plate heat exchanger after the gas cooler, because it is not good to suck gas which is on the saturated line, because every pressure drop what you can have in the suction line, you will immediately get into the mixing area, and then you will not have significant superheat in front of the compressor. So in principle, this is a standard. You have to have a plate heat exchanger in front of the parallel compressors. And here you can see direct influence of ejector operation. On the left curve, depending on ambient temperature, you can see how compressors are changing its loads. This compressor capacity, this is a measurement in our PEC controller about how many compressors of maximum configured compressors in this line are in operation. And you can notice the trend line goes from, let's say, around the 30-ish percentage up to the 70%, let's say. Parallel compressors are starting to operate at around 21, 22 degrees Celsius, and you can see by higher temperature, you have more and more gas in the receiver, and of course, they are working more and more. When we apply combi ejector, it's obvious that in that area here, the system is working very similar, but when the higher ambient temperatures, when HP ejector is capable to lift more gas, you can see decline of empty compressor operation. And actually we are moving this gas from the empty compressor to the parallel compressors. And you can see, of course, much more dots here in the parallel compressors going even to the 100% load. But also what is very good to note, that starting point is much lower. So it means the IT compressor starts here at around 22 degrees Celsius, and here are starting around 17 degrees Celsius. Why is this important? Because you will gain benefits of this technology in more hours in the year because of capabilities to start IT compressors at lower ambient conditions. You have to understand that the temperature out of the gas cooler is directly related to the ambient temperature measurement. When we summarize all these compressor loads, we can show following measurements, and these are power meter measurements, what we have on all compressors summarized in these diagrams, where you can see this gray line shows a standard system with parallel compressors. Then you can see gain of HP ejector operation. And then with the current measurements, what we have, we also see gain utilizing liquid ejectors and calm solution together with HP ejector. And what we believe this is a super good solution, and we on purpose say that we, in our further calculation, what I will show you, we will count that this line will be like this. So this is a dotted line, calculated line, what we are using, assuming that we will not gain such good measurements, but at the end we will gain a significant energy savings. Of course, you will see later on, we will continue these measurements also during this year. So we will gain also the measurements with the higher ambient condition, also utilizing both ejector technology. So we will have a much better knowledge about this curve here. Anyway, these are the models what we are using for further calculation on our energy analysis, yearly energy analysis. The plant is positioned in Germany, next to the Düsseldorf area, and these are the weather profile for the Düsseldorf, where you can see how many hours in the year you have a certain temperature in that year, and you can see that the majority of the hours it's in between 0 degree and 20 degrees Celsius. And for our case, you have to understand that, again, HP ejector is valid for this operation. I mean, when you have 17 degrees and higher ambient condition, and concerning liquid ejector operation, the benefits you are gaining all year round. If you summarize operation through the year for every hour, so it means 8,670 points during the year, we can summarize how many kilowatts hour we consume with both operations during the year. And you can notice also the energy savings in the kilowatt hours, but also in the percentage wise. You can also note that the major savings we are gaining in the summertime operation. If we calculate the price for the electricity on the level of 0.18 euro per kilowatt hours, we are gaining that this system is saving around 1,200 euros per year. Please note that this system is relatively medium-sized supermarket, so it's 70 kilowatts on empty evaporators and 16 kilowatts on LT evaporators. If you have a bigger system, of course, you have a similar savings or higher savings, but the value here will be higher, of course. Summary. This analysis shows that even in a mild Central Europe climate, so it's climate what I show has a majority temperatures between 0 and 20 degrees Celsius, ejectors can bring additional energy savings to the systems utilizing both technologies, HP and liquid ejector, utilizing calm solution. This system is a perfect solution for the medium-sized system with parallel compressors. What I would like to emphasize once again, this analysis were done without heat recovery operation, and this system has a heat recovery operation. So these savings, what you see here, is simply excluded heat recovery operation mode. So we are expecting, of course, that we will gain additional savings when we will use complete analysis, including the heat recovery operation. We are continuing this analysis. Now we are gathering data for the heating season, and in the next sessions, we will also present those results. If you would like to learn more, we would like to invite you to visit our multi-ejector solution website.
Yes.
The link is here. This is how it looks. Now I will start going out of the presentation mode. And here it's the site. Anya will give you some notes around the site. Please, Anya.
Yes, please. So here you see our multi-ejector solution website that is available on the Danfoss website. So it's open for everybody to go in and have a look. Please visit. You'll be able to see a 3D model if you click the red bar there, and you'll be able to see the video that is introducing this solution that you can do for yourself. If you go further down the page, then you will see a short explanation about all 4 models that we have, where today we have been focusing on the combi ejector. You will be able to read more about CAM, or CO2 adaptive liquid management, as Mark have introduced for you today. If you want to know more about a specific product, here on the product range, you can go in and click and go directly into our product store, where you can download data sheets and manuals and all of this for all components that is needed for the full solution. And the next part here is really important. So if you try to click here, Mark, or open it in the top, this is how you choose the right multi-ejector, because what Mark has introduced for you today is how it would look like in a mid-European, Central European climate. But wherever you are in the world, you have to consider which one fits for you best. So there's 3 simple questions. The first one is, what is the ambient condition where you are? Is it warm? Is it cold? Number 2 is, what kind of systems are you familiar with? Are you familiar with working with parallel compression, or do you feel good about a booster? Or you want to go all the way and try to include a liquid ejector, which can be in both a booster or a parallel compression system? So that is question number 2. Question number 3 is, what store type is it you're looking at? Are you looking at a small shop from 40 kilowatt of cooling capacity to a mini market, to a supermarket, all the way up to a hypermarket? Because all of this will determine what model of ejectors will fit your need. So if you scroll down a bit or flip the page in reality, then we have the answer to the 3 questions. And that is that we have 4 great ejector solutions that has different capabilities and fits to different needs. So we have the high pressure ejector block on its own. We have the low pressure ejector block on its own. We have the liquid ejector block. And then we have the combi block that Mark have just presented for you today. And here at the bottom of the page, you have the overview of, depending on where you are in the world, what kind of situation and what your preference is, what block is it we recommend you to use. So please go in and visit the website and have a look at this little guide just to get started. And if we go back to the main website, yes, then we scroll down a little bit more. And of course, we also have a lot of different documents for you to learn more about the ejector solution. And one of those that I would like to highlight is this application guide for high pressure and liquid ejector. So if Mark scrolls down here, you will see that he has created quite a comprehensive document explaining all the steps you need to be aware of when you are working with ejectors. And you can see here he's taking it very thoroughly, step by step, going into details for different application modes, different ambient conditions, considering the differences between MMS and ALC, and so on and so forth. So a lot of these things, as you can see here, you can find on our website and have a better explanation of. So a very good document he has created together with colleagues to explain more in detail about the ejector applications. So I recommend you to go in and visit that. And if we go back to the website, then another recommendation is to visit our Cool Selector software and simply download it. It's free. So go in here, follow the link, and download it to the website, to your own computer, and start working with it. Mark has also conducted 2 very nice webinars that you can see that is linked to right here. One, where he's introducing our new CO2 transcritical high pressure application. So simply a version or a area in the Cool Selector tool where you can go in and select ejectors and other valves and other components to fit exactly the system that you are having in mind. The other one here is explaining how you're working with multi-ejector solutions in general in Cool Selector. So I can really recommend these 2 webinars that are there for free, as you can see. Another thing to be recommended is our Danfoss Learning platform. So if you click that red button there, you will be taken to the Danfoss Learning site where you can go in and just simply register with your email address. And then you can search for all the different modules we have around CO2, around ejectors, and so on. So just go in and search, and you can start getting more modules. And if you wish to see more, we have a lot of support videos, as you can see here, from different product managers, and also a supermarket case here. So a strong recommendation from my side, go in and visit our ejector site because you will find a lot of really relevant material.
Thank you, Anja. With your last word, I would like to thank you for listening us. And if you have any questions regarding our components in CO2, please contact your local Danfoss organization, and we will try to support you as best as possible. Thank you once again. Bye.
Thank you. Bye.